the chair of the first seminary within the project Nanoscale broadband spin transfer torque microwave detector from the program of scientific and technological cooperation between Italy and China. The project is founded by the Ministero degli Affari Esteri e della Cooperazione Internazionale. We are in the Aula Magna of the Department of Engineering of the University of Messina, Italy, and we have the pleasure to host the two principal investigators of this project, Professor Giovanni Finocchio from the Department of Mathematical and Computer Sciences, Physical Sciences and Earth Sciences of this university, and Professor Zhongming Zeng from the Suzhou Institute of Nano-tech and Nano-bionics of China. We are going to start with a brief history of this cooperation by Professor Giovanni Finocchio, and then with a seminary given by Professor Zeng. So Professor Finocchio, would you start with a brief history of this cooperation?
Yes, thank you, Vito, for the introduction. We had basically meet each other in 2012 in a conference in the United States. At the time was the conference of magnetism and magnetic materials, one of the largest conferences on magnetism worldwide. And at the time, I remember that with Professor Zeng we discussed some experimental data he got from his measurements. And we started a collaboration where Messina worked on the theory about this data, while Professor Zeng worked on the experimental part. And after this first meeting in this conference, we have a lot of exchange of emails. And at the end, this paper, this data, this theory was accepted for publication in a very important paper at CS Nano. After that, our collaboration continued for a few years, up to now. I was in China in 2013, where we discussed other two different projects. At the time, we have very nice results about oscillator without any external field, and we were able to find out the oscillator with the lowest critical current. And we wrote other two papers, and these two papers were published in scientific reports in Nanoscale, which is one of the most important journals of chemistry. And then, 2 years later, we got very interesting results on a different kind of device, which is a manual detector, but Zhongming will give all the details about our last finding. And I was also again in China for 1 month in last year, discussing about those results. And it was very nice to have this new paper published in Nature Communication. So I hope that with this project we can continue this collaboration for the next 3 years and also beyond, in order to have very nice results on Spintronics.
Thank you. And now let's welcome Professor Zeng. It's a great pleasure to have you here. We are going to listen to his seminary entitled Spintronic Devices for Applications in Energy Harvesting and Microwave Detectors. Thank you.
So, first of all, I'd like to thank Professor Giovanni to invite me to here. So, as Professor Giovanni mentioned, we have very long cooperation time. So, we already published several papers in spin microwave detectors or devices. So, today, I'd like to give a short introduction of Institute and then present one typical results based on our cooperations. So first, I'd like to show you a little about the Suzhou Institute. As we know, Suzhou is a very good city. We have is near to Shanghai. If we see the map, it's very close to Shanghai. We just a half-hour driving to Suzhou. Also, we can see Suzhou is similar to Venice in Italy. There are lots of river and lakes. So also there are lots of gardens. Also, Suzhou is very famous about the circus. Also, we can see the labs of the typical maps. There are lots of silk. Also, Marco Polo also have visited Suzhou. So let us show you present about our institute. Actually, our institute is a new institute, but have a very good facility. We hope to build an institute on nanotechnology and nanobiologicals. So for the first stage, with the government invested around $200 million to build this institute. And now we have 500 staffs, and most of those staffs have a broad experience, for example, in US, Japan, and Europe. So we are the youngest institute, but we have good facility that I show you. Most of our research field we focus on is nanotechnology. So we have different distributions for the nano devices or nanobiological. Also, we have some cooperation with the University of Messina in biological, except our cooperation in physics. So maybe 2 years ago, also the director of University of Messina have been to Suzhou Institute. They already signed some agreement for future cooperations. So in the future, maybe both sides will enhance the cooperation. Also, Suzhou have a very good industry park. So some following teachers or some research, they can provide technique to Suzhou. Maybe they can fund a company in Suzhou. Yeah, so it's a very good place to make the technique into commercial product. So here is the research of our institute. Also have some branch of nano safety. This is also use nano material and nano devices to focus on the safety. Also, we have some system integrations for semiconductor nanotechnology. Also, we have several platforms for testing, analysis, or engineer development. So here I show you the basic of our nanofabricators facility. We have 5,500 square meter clean room. So we have lots of clean room stuff or instruments. For example, we can grow any kind of materials from metal or semiconductor or other dielectric materials. So we have different tools. Most of our tools have very good performance. So we can do doing some basic research. We also can do commercial stuff. So here we have different lithography systems. For example, for the EB lithography system, the resolution can be done to 8 nanometer. So That's very important for nano devices fabrications. Later I'll show you our fabrication process. Also, we have etching facility. If we want to transfer the pattern to the devices, this is also necessary. So here we also have some package. Once we finish the device fabrication, we want to package the devices into that measurements or calculators. So here we just show you the several typical products we can fabricate high efficiency solar cell. This is very good for green energy. So there are several research have already developed this technique into product. So also we have high terahertz detectors for terahertz applications. We also have radiation detectors or MEMS or LED. Also we have MEMS microphone. So for example, for Apple cell phone or Samsung cell phone, some they already use the MEMS microphone. So there are several copies already by MEMS microphone from the company that belong to our institute. So the second part is our major topic today. So I will show you the typical results in microwave detections. Actually, as Professor Giovanni mentioned, we have already cooperation in several directions. For example, speed transfer, torque, outbound oscillators, or memories. But today I just talk about the energy conveys in microwave detectors. So before start, maybe I'd like to give a simple introduction of the Spintronics. What's the Spintronics? As we know, in traditional semiconductor technology, usually we move the charge. For example, we use the charge to electronics. That is very important for current technique. So, for example, we use the semiconductor to develop the transistor. So, however, this have a very big issue in conventional semiconductor electronics. One issue is the power consumptions. When the devices the size down to nano size, the power consumption increase a lot. The second is basically that device is voluntary. It means when we shut down the power, the information will lost. So now there are new way. If we, as we know, the electron have two basic attributes. One is a charge, another is the speed. So if we can utilize the speed, so we can enhance the device function. So for example, most important to extend is a magnet resistance. So use this technique, we can develop the magnetic recording. So for example, this have a lot of applications. So here I show you this giant magnetic resistance. So actually this phenomena was discovered by two scientists. One is Peter Puliafito, another is Affari. They observed in this phenomenon in 1988. So just after 5 years, the IBM company can develop this technique to develop hard disk driver, increase the the hardest discover. So in 2007, the Nobel Prize just awarded him for the discovery of general magnetic resistance. Except, as we know, there are lots of applications for Spintronics devices. For example, this hard discover is already commercialized. Also, is the sensors. The magnetic sensors have lots of very wide application in our daily life. For example, there are lots of sensors in our vehicle. Also, there are several different contributions. But for us, we talk about today, we mostly focus on the microwave devices. This is very important for our future macro wireless communications. So before I'd like to give a very simple memory of magnetic memories. As we know, these magnetic structures include, typically these devices include 3 layers. 2 magnetic layers are separated by insulator or spacer. This spacer also can be metal. So the resistance of devices depends on the orientation of 2 magnets. Because the magnetization are allied parallel, so the device's resistance will be low. Sorry about it, we made a mistake here. But if it's unparallel, the resistance will be high. So we can use this as a digital one. So we use this kind of technique for memories. For example, here we can build a memory array. So to realize the storage. Now there are lots of companies to work on this field. Also, and I'm show you this memory have very good advantage of over traditional memories. For example, MRAM have very low energy. For example, if we run beer for conventional devices, the run energy is very large. 2 gigajoule or even nanojoule. But for MRAM, so the run energy is very low. It's just 1 to 2 gigajoule. We did a lot of work on this field, but then I don't have enough time to show that. In the future, maybe we can use this memory in our daily life, especially in cell phone, because if we include this memory in a cell phone, we save a lot of energy. So we don't need a charge every day. So there are huge memory market. The American company give just estimation, maybe 600 billion US dollars. So also recently I just read the news, a US company is ASD. They already developed one MRAM for 1 gigabit. So they already use this MRAM into cell phone or some MP4 devices. Also, except the memory, as we mentioned before, if we can drive the magnetization oscillate, we can use this technique to make some microwave devices. So here is the basic ideas. When the AC current is applied to the devices, can produce the phase oscillation. So because this is a magnetic resistance device, so this device can transfer the AC voltage to DC voltage. So it means we can use this for microwave detection, because the detection frequency is around gigahertz. So it's very important. So for practical application for this device have very large frequency tunability. As we know, most of micro devices used in commercial is sharply dialed. The frequency tunability is just 20%, so it's a little bit limited. But for this magnetic devices, the frequency tunability is very large, can be from several hundreds hertz to gigahertz, so it's very important. Also, the frequency controlled by field, also can by current. Also, they are small size. That I show you. Also, the power consumption is very low. Also, this micro device have lots of advantages, but however, there are some fundamental physical depend of the device are needed to resolve. For example, the detector sensitivity is not so high right now. Also, if we want to detect a microwave, we need additional magnetic field. So this is undesirable for on-chip application. So from this point, we design some instruction. We already observed the good results in this field. So here I will show you in details our progress and the challenge. For example, as I mentioned before, the most important is since it has very low detection sensitivity. For the first experiment, just 1 milliwatts, so it's very low. Also, there are several groups have already improved the detection sensitivity, but still a little bit low. Also, they trying to use different methods. One is just to change the magnetic field direction or magnetic amplitude to tune the detector sensitivity. For example, they already use another technique is called nonlinear or resonance technique. They observe a very high detector sensitivity, but we can see they only can observe the good results at low temperature. However, this is not good for practical applications. In 2014, when Japanese group, they observed a very large detection sensitivity. However, they need to apply the Pacific field in particular directions with particularly amplitude. For this one, we think is hardest. It's not a practical for applications. For our understanding that we should to achieve high detection sensitivity without magnetic field. So we, from this man, we build some devices. We design a magnetic junction. So firstly, we design this junction first. Then Professor Giovanni also did some macro simulations. His simulations found out this junction is very good for for macro detections. So after that, we use PVD systems to grow these structures. So then we use a magnetic technique to align this sample. Then we get the very good parameters devices. For example, at first we use these devices to fabricate the speed transfer torque devices. Also, we upload the microwave emission at the magnetic field. So we have already published in one paper in SS Nano and another paper in scientific report. That's about the nano oscillator. So here I show you how to fabricate these devices. For nanoscale devices, the fabrication process is a little bit complicated. This process includes several steps of electron beam pattern or etching or metal or dielectrical deposition. So usually if we fabricate one device, we need around 1 week. Yeah. Also, because of the size is very small, so the yield is not so high. For example, if we fabricate 1,000 devices, maybe we can get maybe 800 or 600 devices. But innovation is very good for basic research. So here is our basic measurement. We introduce the microwave source, then we use the locking amplifier to measure the response of DC. So here is the basic performance. First of all, we check the basic transport, because this is a magnetic resistance devices. First, we check the resistance with the field. We can see if the change is large, it means the device is very good. So, in principle, the largest change we can upload is around 100%. So, here this will show you the change with the field. So when we sweep the magnetic field, the resistance gradually change. It means the Freening magnetization is gradually change with our magnetic field. Also, we did the microwave detection. So first of all, because we hope to observe this performance in absence of the magnetic field. That's important, as I mentioned before. So fortunately, we got a very good response. For example, we had a very small AC current. For example, when the AC current is just 0.1 megawatt, it's just 10 nanowatts. We upload a very high detector sensitivity, is about around 1,000. This is comparable to the Shockley dioxide detectors. However, for this semiconductor detectors, they can't work on the microwatts. They only work maybe in that from microwatt to milliwatts. So in the future, if we they want to improve the detector limit. So this spin device is a very good alternative approach. So also very important, we found this type of performance can further enhanced by applied DC values. We can see without DC, the detector sensitivity is around 1,000. Interestingly, if we applied different DC voltage, we found that the detection sensitivity can be significantly enhanced. For example, at the minus 0.5 microampere, the detection sensitivity increased almost 20 times, so around to 75,000 microwatts. So it's very good. Also, is a record. Is a record. So. So we want to try to understand why these devices have very good performance. We did some simulations. Professor Giovanni did simulations. They found they are very interesting mechanism. So we found is a injection lock. Plays a very important role in enhance the detections. So here I show you several data. We can see when the frequency, the external frequency is the injection in the devices, because also the devices also is in top microwave device. Because when we apply the DC current can produce oscillation. So this oscillation is marked with an external frequency. So, for example, in the lock range, the detection voltage enhance a lot. So here is just to show you the lock range. So for example, for this particular devices, the lock range is just 40 megahertz. But of course, let us show you the experiment data. If we increase the microwave power, we can increase the lock range. So here, after that, we did the experiment to verify this injection lock. So here is the experiment data. For example, we introduce the external microwave wave, then we change the current, because the current produces the microwave. So we indeed see the lock range. Also, we can see in the lock range we see the very narrow oscillation peaks. Also, we see the detection voltage. We can see in the lock range, the detection voltage can be up to 20 milliwatts. So it's very large. We can see the power is just 1 megawatt. So the detection sensitivity is very large. Also we can see the lock range increase with the microwave input powers. So in the future, in our Journey program, we will continue to work on this project. We hope to get the very broad microwave detection, because here is just 100 megahertz. For broad application, we hope to obtain maybe megahertz, maybe 1,000 megahertz detections. So we will continue to work on this. Recently, we got some initial results, but we didn't show here, but it's very promising. So finally, I'd like to give a small summary. We already demonstrated this ultra-high detection sensitivity in microwave devices. For example, the detection sensitivity can be up to 75,000 microwave per megawatts. So it's almost 20 times than of semiconductor counter devices. Also, we can see the power is very low. It's just less than 10 megawatts. So it's very good for green, for energy future, we think this could represent a new road for develop next generation on-chip microwave detectors. So, actually, it's very important for this talk. You know that if we want to further enhance the performance, we need to continue to provide a new technique. So very good news. We have very good collaborators. For example, Professor Giovanni is an expert in theoretics. So that's very important for our project. Also, we have another cooperations from USA. So we can discuss the progress, especially in experiment set. But for theoretical, most of it is done by Professor Giovanni. So this is a very good teamwork. So thank you very much.
Thank you, Professor Zeng, for this very interesting seminary. The seminary is open for discussion, but before I would like to take advantage of this moment to remind you that next Wednesday, 15th, we will host the annual meeting of the IEEE Magnetics Society, and Professor Zeng will give a conference call with another talk. Thank you again, and now seminary is open for discussion if anybody wants to ask something.
I have just a question. Do you think how you can control exactly the thickness of the free layer? Because I see that it's very real value.
Okay, so that's a very is a technical issue. Actually, we usually it's difficult to control the thickness in astro, right? But in our instruments, we can grow a large sample. It means the free layer can be gradually changed. At the first stage, so we grow a large chip. Then we optimize the thickness. After that, we can grow a uniform free layers. As we know, we have very good instruments. This instrument can grow very slowly. For example, the growth rate is about 1 astron per second. So we can control the thickness precisely. So that this is very important. In this structure, as Professor Zhongming mentioned, the thickness is very important for obtaining the high performance. If the thickness is less than 2 nanometers, the performance will change. But we can control.
Any more questions?